Today, we're going to look at how to calculate concentrations at equilibrium conditions given initial conditions. So in a lot of cases, what we're going to know is what's true at the beginning of a reaction. For example, maybe you fill a reaction vessel with 1 molar of some compound, let's say hydrogen iodide gas, and you're interested in, if I leave this thing here at this particular temperature and this pressure or molarity that I've got it at, over time, what will the concentration eventually be of my starting gas and then the product gases, in this case hydrogen and iodine gas? Now, to get there, we've got to figure out how to get to the equilibrium state. So the initial conditions are not necessarily going to match equilibrium. In many cases, they won't. So what we need to do is we need to see how much change occurs between those two. And from these 3 categories, we get the name of the table we're going to use to help solve these. It's called an ICE table. So we start with our initial conditions, we look at how much change should occur, and we look at what it'll be at equilibrium. The easiest way to do this is to actually do an example problem rather than just try to talk through it in words. So let's start with an example. I have 3 total we're going to look at. So we'll start with this problem. Consider the reaction A is at equilibrium with B, and it has a Kc value of 2. If a chemist fills up a reaction vessel with 1 molar A and no B initially, what will be the concentration of A and B at equilibrium? So let's figure that out. So we start by filling up our initial conditions. I'll just write an I here. And initially, there's 1 molar A. So I'll put 1.00. And B, we don't have any initially. So that would be 0. Now, under the change category, what we're going to say is that the reaction is going to happen X times. So you don't have to write this part every time. This is just to explain what I mean by X. So we say the reaction happens X times. So we need to decide how much each is going to change. In this is our simplest level of reaction. It's a single molecule turns into a single different molecule. So it's a 1-to-1 reaction. So every time you use up an A, you make a B. If you were to go the other way, remember we have the double arrows, the reaction can go both ways. So if you use up one B, you make one A. So we just have to account for that. So both of these are going to change by the number of times the reaction happens. Now in this case, there are some A molecules at the beginning and there are no B molecules. So I can't make any more A. So I know I'm going to have A be the molecules that I use up. So this change is going to be minus X. And then B is going to be plus X. Now if it had been 2B, it would have been plus 2X. If it had a 3A, it would be minus 3X. Also, in some cases, you might have some A and some B, and then the reaction can go either way. Over time, you can usually get a feel based on the K which way it's likely to go. But if you're uncertain, it's okay to just assign minus and plus to one side. In the end, you might just get a negative answer that when you plug back in, then gives you positive values. What we know is at the very end, our concentrations need to be positive. We aren't going to have negative half a molar concentration of something. We don't have negative molarity. That wouldn't mean anything reasonable here. So what we do is we say, okay, this is how much it's going to change. And just make sure that one side is all negative and one side is all positive. However you want to define it, just be consistent. And by one side, I mean, sometimes you're going to have more than just B. Maybe you have B plus C. Then you have a plus X for B and a plus X for C. You wouldn't have a plus X and then a minus X if both of them were on the same side. And we'll look at some examples with more than 2 things momentarily. So finally, I need to set up my equilibrium conditions. So this will be 1 minus X. And then B is 0 plus X. So we're just literally adding up what's the initial condition, how much did it change by? Well, that's where it's got to be at equilibrium. So we have 1 minus X for A and X for B. The way we solve this is because we know our equilibrium constant up here. So K is equal to products over reactants, and it's Kc, so it'll be concentrations. So we'll have the molarity of B over the molarity of A. So that will be X over 1 minus X. And this is all equal to 2. Put a line there, we'll start over up here. So now I just have to solve for X. So I multiply both sides by 1 minus X, and I get X equals 2 times 1 minus X. We distribute the 2. I get X equals 2 minus 2X. I move that to the other side. I have 3X equals 2. And so I have X equals 2/3 or 0.67. Now, we're not done here. So some people will actually just circle this answer and be like, okay, we're done. We have 0.67. But we have to actually come up with what are those concentrations. So let's plug them in. Get this back. So it is true for B. B is just 0.67. That's good. But then A, we have to go back to our equilibrium equation, which is 1 minus X. So we have 1 minus 0.67. So that'll give us 0.33 molar. So that's our concentration of A. That's our concentration of B. So just make sure you account for the equations you actually have. Sometimes you might have a 2x. Maybe you need to double it. So X is when you're almost done, but not quite. You still have a little bit more to do there. Now, we're going to look at a second example that's going to be a bit more work. And then after that, we'll look at how to shrink these problems in a lot of cases. So this problem is we have some actual reactants. We have 2HI is in equilibrium with H2 plus I2 with a Kc of 0.016 and a temperature of 800 Kelvin. Note, you're going to see these temperatures a lot, and it's not because you're going to put them in an equation anywhere. It's because equilibriums are temperature dependent. The equilibrium is going to shift if you change the temperature. So because we want to be scientifically accurate, we're going to include the temperature for that. Don't freak out, though, and go, oh my gosh, I didn't put it in an equation. I must have missed something. No, you did. You're okay. I know that part can be hard at first. It's using learning how to process things that feel like extra information. So for the trained chemists, they're like, no, that's something you need to know. It's where the equilibrium is true at. It's not true at all temperatures. But for your problem-solving mind, it might be like, oh, but I didn't put it in an equation. That's okay. Don't let that stress you. There are some equations we'll get to eventually where you can use temperature to figure out some stuff with K as you change temperature, but right now we won't worry about it. There are times where you use it, but for now, we're just going to say it's something there we know. So we have the equilibrium, and we're told if a reaction vessel initially contains 0.5 molar HI and no hydrogen or iodine gas, what would be the concentration of all reactants or products in equilibrium? So this problem might not look that much different, but the math's going to take a little more involvement here. I will note, if you've done some of these problems before and you're seeing my examples of the second one, there is a shortcut we could take here technically, but we're not going to do that because I'm going to show us how to do this the way that works for more types of problems. And then the next problem we'll look at, okay, what's a shortcut we can take to shrink how much work there is? So I promise they won't all be this long. So I mentioned that because initially I think this will look like, oh my gosh, Dr. Leslie, how am I ever going to solve these on a test? Which you can, but we won't do all of them like this. So we'll set up our ice table again. So we have 0.500 of this, and we have none of the products. Now, I'm using up 2HI every time I do a reaction. So this is now minus 2x. It's not just minus x, because I use up 2HI molecules. I just had a hand motion and realized nobody could see it. I'll just scoot myself over. There we go. So yeah, when we go from HI to do the products, we're using up 2 every time, so we need a minus 2x. Now these, on the other hand, will be plus x and plus x because we only use one of them. We only make one of them each time we do the reaction. So we have 0.5 minus 2x, x at x. So now let's set up our Kc, and you'll see why there's going to be a little bit more involved here. So we have products over reactants. That's H2 times I2 divided by HI squared. And remember, you have to put the square here if there's a 2 there. So even though you have a 2x that's related to that 2, you also have to put the square or the cube or whatever value it would be appropriate. Don't forget that part. It's easy to be like, oh, I said minus 2x. I'd already accounted for it. Nope, have to do it in both places. So in the top, we have x times x for H2 and I2, so we just have x squared. And then bottom, we have 0.5 minus 2x squared. And this is all equal to 0.016. Now, I'm going to solve this a slightly longer way. There is a math shortcut you could use in exactly this case where you square root both sides because the 2 squareds would cancel out. However, you'll have a number of problems where that's not doable because one of the parts isn't going to be easy to square. Maybe you only have one product on one side, or maybe you have 2 different starting concentrations of something. So don't assume you can always solve it that way. It's a quick math trick you can use to speed up this problem, but I'm going to show you how to do it assuming you couldn't do that. So I'm going to FOIL out the bottom. So when I do that, I'm going to get that x squared over 0.25 minus 2x plus 4x squared is equal to 0.016. Oh, my face is blocking the way. Sorry about that. There we go. So I've got that. And now I need to solve for x. So we got some movement to do. So go to another slide. But I can come back. So now I'm just going to rearrange that equation. Well, I'll rewrite it here so you know what I'm working with. Our x squared over 0.25 minus 2x plus 4x squared equals 0.016. Then I'm going to multiply by the denominator, and I'll get x squared equals 0.016 times this stuff. Note that if you're solving this on your own, like in my class, for example, I'd be perfectly happy for someone to just go ahead and multiply that out. I'm just writing some extra steps in between a little bit to help you track so you don't get lost. Long term, I think it's good if you can move and multiply at the same time. It's perfectly reasonable. But for now, this will help out. So then I distribute my 0.016 times all of it, and I get 0.0040 minus 0.032x plus 0.064x squared. Now, since I have an x squared and an x term, I can use the quadratic equation to solve this, but to use the quadratic equation, I have to move everything to one side and set it equal to 0. So I'm going to subtract everything on the right side from the left side. So when I do that, I get 0.936x squared. As a reminder, this x squared has an understood 1 in front of it, so I did 1 minus 0.064 to get there. Then I had to add 0.032x to both sides, and then I had to subtract 0.0040. And this is all equal to 0. At that point, we can use our quadratic formula with a reminder that this is a, this value is b, and this value, including the sign, is c. Don't forget your negatives. So x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's our quadratic formula. So now we have to plug our values in. And so let's see, we have negative 0.32, because it's negative b, plus or minus the square root of b squared, so, or sorry, did I forget a 0 in there? No, 0.32 is okay. Tracking something real quick. I think I Ooh, I'm going to have to fix that in my own solution. So I accidentally dropped the 0 when I was solving earlier, so this will take me a little longer, but we have a 0.032. There we go. So we have 0.032 squared, and now 0.032. Okay, so then we've got that, and then we have to subtract 4 times 0.936 times negative 0.0040. And obviously on your paper, give yourself a little more room than I did just there. And then we're dividing all this and by 2 times 0.936. So this will give me negative 0.032 plus or minus these. I'll just get the value of the square root. I got was 0.1265. I kept a few extra digits in the middle because I don't want to round too much early on. We'll round to around, let's see, 3 significant figures at the end. The decibel's going away. So 0.032 plus or minus 0.1265 divided by, let's see, what's that? Calculator, had to get the value right. So 2 times 0.936 is 1.872. So this is what is equal to x. So you get two values. X is equal to either 0.0505 or negative 0.0847. Now, if we go back to our ICE table, and I'm going to come back to this slide, I'm just going to go here real quick. These are the equations we have to plug things into. And notice, if you had a negative value for x here, you had negative concentrations for H2 and I2. When you use our quadratic formula, usually one of the values will end up giving you negative concentrations, so that's how you know that answer can't be right. That is not a good answer. Note that depending on the way you set up your equilibrium equations, it might not always be the negative x. It could potentially be that x should be negative somewhere, especially when you have both products and reactants at the start rather than just one. It makes it more likely for that to happen. So make sure to check both answers. Don't just assume positive x good, negative x bad. Plug them into equilibrium and see which gives you all positive concentrations. And then that's the one you'll go with. So now, when we plug that back in, so the problem asked us to find all the values. So first we have our equation for HI, which is 0.500 minus 2x. And we're using this value here since the other one gave us negative concentrations. But if you're not sure, just plug them both in and try them all. And when you do that, you plug that in for x, you're going to get 0.399 molar. That's my HI concentration. Now in this case, H2 and I2 are the same thing because they're both equal to x. And so that's going to be equal to 0.0505 molar. And so that's going to be my H2 and I2 concentrations. So those are our final answer. We have our concentrations for HI is 0.399 and H2 and I2 is 0.0505. So with that can help us figure out what we were trying to get for our concentrations. You'll notice I know that was a lot of work. Sometimes you'll be able to skip over some stuff. For example, in this one, you could have taken a square root and solved some of these problems, but also sometimes there just isn't going to be a big enough effect on the equation for x to matter in all instances. Now, what do I mean by that? How could x not matter sometimes? Let's take a look at an example. So consider the reaction 2H2S reacts to form 2H2 plus S2 with a Kc of 1.67 times 10 to the negative 7th. And we're given some information about the reaction. We're initially at 0.1 molar H2S, and we want to find the equilibrium concentrations of the products, H2 and S2. What's important here is look at this value for Kc. It's 10 to the negative 7th. If you remember from our definitions of K, what that means is that because Kc is so small, remember as that becomes more and more negative, it becomes a smaller and smaller number. Once we get to values like this, then K is probably going to lead to where almost everything stays as a reactant. Very, very few products form. Now, why might this matter? Let's take a look. So, we have our initial conditions, 0.100 molar, 0 and 0. Our change is going to be minus 2x plus 2x plus x. And our equilibrium is going to be 0.100 minus 2x, 2x, and x. So initially this looks a lot like the other one, and it's actually going to be even more work. There would be an x cubed somewhere in here. It would be hard to solve. But when Kc gets sufficiently small, and it depends on your concentrations exactly what this is, but a good rule of thumb in my book is like when you start getting to like 10 to the negative 4, 10 to the negative 5th, there's a very good chance that x is small. And as you solve more of these problems, you'll get a more intuitive feel for where that is. It is dependent on concentration, so as concentrations get smaller, technically Kc needs to get even smaller for x to be small. But our question is, what does x being small do for us? Well, if you take 0.1 and subtract a very small number, it doesn't change it. So if x is small, we can ignore any time x is added or subtracted from a number. Now, we don't know the answer yet, but imagine the answer was x is 1 times 10 to the negative 8th. If I take 0.1 and I subtract 2 times 10 to the negative 8th from it, and I round it to the right number of sig figs, I still have 0.1. It didn't change the number. That means x just didn't matter in that case. So I can do that anytime I'm subtracting or adding an x to another number that isn't 0. Now, in the case of the H2 and the S2, I can't do that because I'm adding it to 0. It would still show up. It would still be relevant within our significant figures. And at the end of a problem, when you think this is true, because of how much time it saves, it's worth it solving it, assuming x is small. Then at the end, you plug the value back in, you look at the value you get, and you see, if x weren't small and I plugged in my equilibrium concentration, does it change the value by more than 5%? That's sort of that's the barrier to entry we give. If it's less than a 5% change, I was right. X was small enough that I can just not worry about it. There are other ways to solve these, but this is the main one we're going to use here. This is the main shortcut. There's some other stuff you can do, but this is the one we're going to focus on. And this is relevant because there are a lot of problems, especially as you get towards the acids and base chapters that follow this, where you have very, very small Kcs. So there are a lot of conditions where this is a reasonable assumption. So we bring it up because it comes up a lot, and it saves you a lot of time. So now let's set up our Kc and assume x is small and see what it does. So we have H2 squared times S2 all over H2S squared. And we'll plug in our values. We have 2x quantity squared. Don't forget to square the 2 and the x. It's important. We multiply it times x, and then we're divided by 0.100 squared. Now, when I do all those values, the top 2x squared is 4x squared. 2x quantity squared gives me 4x squared times x gives me 4x cubed divided by 0.0100. That's when I squared 0.1. And this is all equal to 1.67 times 10 to the negative 7th. Now, on the next slide, I'm just going to multiply both sides by 0.01. So my top is still the same. Let me get that. I have 4x cubed. And now I have it equal to 1.67 times 10 to the negative 9th. I multiply both sides by 0.01. Then I want to get x by itself, so I divide by 4. And that gives me x cubed is equal to 4.18 times 10 to the negative 10th. Now I need to get rid of that cube. You can either do the cube root of it, or what I like just putting in my calculator is if I raise it to the 1/3 power, that's the same as taking the cube root. And if I do that to both sides, I get that x is equal to 7.47 times 10 to the negative 4th. Now the problem asks me for the concentration of H2 and S2. So H2 is 2 times x. And if I double that number, I get 1.49 times 10 to the negative 3 molar. And then we get S2 is equal to 7.47 times 10 to the negative 4th molar. So those would be my answers. And then I can go back and check that it was a reasonable assumption that x was small. So my H2S concentration is equal to 0.100 minus 2x. I'm going to put in 2 times 7.47 times 10 to the negative fourth. Let's see what that gives us. Grab my calculator. So we have 7.47, 10 to the negative fourth times 2, and we take 0.1 minus that, and I get 0.0985. Now you'll notice we said 5% was sort of our guiding line. So 5% of 0.95, so 5% lower would have been 0.095. That's just 95% of the value. 5% higher would have been 0.105 molar. This number does not get to either of those extremes, so we say it is a sufficient approximation that this didn't change the number significantly, so we're going to ignore x in this case. So that was a valid assumption. We got our answer. We were able to get our concentrations of H2 and S2. If I'd gotten a value like 0.09, then it would have meant that, okay, this estimate wasn't reasonable. We're going to have to go back and treat x like it isn't small and actually solve the question. So with that, I hope those 3 examples helped you out with trying to solve ice tables. And I wish you all the best. You will continue to do these in our acids and base chapters. We will get lots of practice at these as time goes on. So I know these can feel a little rough when we're first doing them. There's a lot of math to keep track of, but over time, you just keep doing them, and I think these get a lot easier. They're still long, but they just become very systematic, and you just keep applying the same system over and over again, and that practice really helps out with it.